Hi there. So you will notice in Canvas that we are really switching gears here for sort of the end of this week. We're going to chat a little bit about triangles, and a lot of this should be review, but I'm not really sure when some of you have taken geometry or if this was a topic that was covered in your Algebra 2 course. So we're just going to spend a little bit of time this week recapping special right triangles and working with sort of right triangles in general before we get into our trig functions. I think it will build a really nice base for what we will be doing in the following weeks to come. So when we talk about special right triangles, we let's start with a sort of right triangle here that also happens to be isosceles. So when I say it's isosceles, I mean these two, and they're called base angles here. These two angles are equivalent, which also means that the sides that they don't share, so this side and this side, is also equivalent. So let's go ahead and call this side M, and I know that this side is also M because they're equal, and let's call my hypotenuse K. What I want to do with you right now is just come up with the ratios for this 45, 45, 90 triangle. So when we talk about special right triangles, there are two of them that we talk about, one of them being 45, 45, 90. And when we talk about 45, 45, 90, we're talking about the measures of the angles that's inside of the triangle. So I've labeled this triangle. I know that these two legs I can label the same because it's an isosceles triangle, and my hypotenuse is labeled K. So based on my Pythagorean theorem, I know that m squared plus m squared is equal to k squared. And I can simplify this into 2m squared is equal to k squared. Let's come up with a ratio for this side m right here. So let's solve this for m. So I can divide both sides by 2 and get that m squared is equal to k squared over 2. I can take the square root of both sides and get that m is equal to the square root of k squared over 2. So this will leave me with k over the square root of 2. And we know that since I have a radical in the denominator here, that I need to rationalize this. So let's multiply by our fancy version of 1. And here I end up getting that m is equal to k times the square root of 2 over 2. So if I wanted to come up with a ratio where all of these side lengths are sort of in terms of one variable in my 45, 45, 90 triangle, this is k square roots of 2 over 2. And this ends up staying as k. So this is really my big idea here for my 45, 45, 90 triangle. So we'll keep this sort of in the back of our mind here. And we'll do some examples in just a little bit. And before we get to that, I want to go ahead and talk about the other special right triangle, which is my 30, 60, 90 triangle. So here, let's go ahead and delete this. We'll delete some of this here. So let's talk about my other special right triangle, which is my 30, 60, 90 triangle. And here I have, not drawn to scale, a 30, 60, and 90 special right triangle. So before we get to this, let's talk about sort of something that's familiar to us of where maybe this 30, 60, 90 triangle could have come from. And let's take a look at an equilateral triangle. So an equilateral triangle, I know that all of my angles are equal and all of my side lengths are equal. So sort of a brief version of this, we could call this a really brief proof here, would be that from this point, I can come in here and drop in an altitude, and knowing the definition of altitude, this creates a 90-degree angle with the opposite side of where the altitude is starting from. And I could go ahead and prove that this triangle here and this triangle here are equivalent triangles. So I know that this side, if this side is x and this side is x and this side is x, then this side over here becomes 1/2 of x. So this is sort of where my 30, 60, 90 triangle is coming from. So here I have this 90-degree, I have this 60-degree angle, this 30-degree angle. There's my 60 cut in half. My hypotenuse is x, which is the side length of the perimeter of the entire equilateral triangle. And I know that I have 1/2 x over here off to the side. So I can again go ahead and use my Pythagorean theorem and say that x over 2 squared plus, let's call this side over here h, plus h squared is equal to x squared. And I can go ahead and I can solve for that side length of h, so I have sides of this triangle labeled here that are all in terms of x. So this gives me x squared over 4 plus h squared is equal to x squared. I can subtract x squared over 4 from both sides. And let's move on up over here. So I'm left with h squared is equal to x squared minus x squared over 4. So let's come in here and call this 4x squared over 4. So I'm making a common denominator. So h squared is equal to 3x squared all over 4. And I'll go ahead and take the square root of both sides. So h is equal to the square root of 3x squared over the square root of 4. So h is equal to x times the square root of 3 all over 2. So here, instead of writing h, I can write x times the square root of 3 all over 2. So this is just a nice sort of brief recap of where these special right triangles sort of come from, where these ratios come from. Again, this should be somewhat of a review for you, and if it's not, and it's something that you have questions about and you want to chat a little further, please reach out to me. I'm more than happy to go into some further detail with you one-on-one. So let's go ahead and do an example here. So here I'm talking about a 30, 60, 90 triangle, and I want to solve for this side length of x right here. So what I can do is I'll come up here and I'll grab my ratio, and I can just have that off to the side there. So looking at this 30, 60, 90 triangle, they're giving me the side or the angle measure of 30. Angle A is 30, so that means that this needs to be 60. And what do I know about my 60-degree angle? What's the relationship here? It's half of the hypotenuse. So if my 60-degree angle, if the side length that's associated with that, so that's this side length right here, is half of the hypotenuse, I know right away that my hypotenuse will be 12. And if 12 is my hypotenuse, I know the relationship between the hypotenuse and this 30-degree side length here is that x times the square root of 3 all over 2, and I know that x is 12, so 12 times the square root of 3 all over 2. So this other side length will be 6 times the square root of 3. And we've just created all three sides of that triangle there. So we have all sort of unknowns figured out. The other thing that I could have done here, so let's go ahead and talk about another way to sort of go about figuring this out, is taking a look here's my 60-degree angle, and here is the piece of information that's given to me, which is 6. I can say that 6 is equal to 1/2 times x. So 6 is equal to my ratio side length. Those two side lengths will be equal since these right triangles are similar. So I just multiply both sides by 2 here. And 12 is equal to x, which is exactly what we had gotten in the first place. So here's 12. 12 is equal to x. And then we can go ahead and use x from there to fill in the rest of the side lengths. Here is an example of a 45, 45, 90 triangle. So something that I know about these 45, 45, 90 triangles is that they are isosceles, so the legs will be the same. So there's really two ways to go about evaluating this. I can come back up here. Oh, I actually erased that. You'll see that here is the 30, 60, 90 ratios that we created. Here is another version of those ratios. But knowing where we're headed with our unit circle, I'm going to come in and sketch here our 45, 45, 90 triangle here. We call this side over here K, and we had K square roots of 2 over 2 and K square roots of 2 over 2. So again, 3 ways to go ahead and do this. One way is to see that this is a right triangle, that I have 2 of the leg side lengths, and why don't I just go ahead and say that 3 squared plus 3 squared is equal to x squared. So 18 is equal to x squared. I can take the square root of both sides and get here that x is equal to 3 square roots of 2. So x is equal to 3 square roots of 2 when I simplify the square root of 18. So that's one way to figure out what this hypotenuse is. The other way is to use my ratios and say here, let's grab another color, this is the ratio of the side length that matches up with this side length over here. So 3 is equal to k square roots of 2 over 2. So 6 is equal to k square roots of 2. Divide both sides by the square root of 2. And so 6 over root 2. And again, we'll rationalize this denominator here. So I end up getting 6 square roots of 2 over 2, which simplifies to 3 square roots of 2, which is exactly what I got using my Pythagorean theorem. So again, there's quite a few ways to do these problems. You'll notice that you'll have some some problems for you to work on that are dealing with special right triangles in this section's homework. And we can chat a little bit about this on Tuesday and Thursday in class as well if you have questions. So good luck, guys, and we will chat soon.